So whatever you're saying isn't really coming through, it seems. My guess would be that you've probably not set up your microphone correctly.
So can you hear me now, please?
Hey, finally.
Can you hear me now?
Yes.
Okay, thanks. Yes, so there is a pipeline. If we need to develop a machine learning model for any system, for solving any problem, we need first to start by, we need to load our data, because it's supervised learning, and in supervised learning, we need to use data, we need to use some features and some target features. Target features or labels, those are the teaching signal which will be used for training. So first we need to upload our data to to your computer, for example. And after that, you need to maybe visualizing your data and try to simplify it as much as possible. So for example, we need to normalize it, we need to standardize it. When we normalize it, it will take values between 0 and 1. It's very important for machine learning because of the activation function which we use. And also because standardization of data, it means all data should have mean value of 0 and standard deviation of 1, for example. And after that, we need to visualize the data. And then when we visualize the data, we can understand what kind of model we can use. We call it model selection. Model selection is very important. So for example, as you can see here, if your data is simple, if your data, for example, looks like this data, it means we can use a simple model for classifying it. For example, if we have two classes, the red class and the green class, it should be easy to understand that, okay, we just need to get a model, and this model should help us to generate a decision line, which is linear, straight line, and this line will be used for classifying our data set, right? So from visualizing the data, it will help us to understand what kind of model we need. So if you have two features, x1 and x2, and if the data is simple and it's linearly separable, in this case, I can just use a perceptron, for example, because I can get this line using a perceptron. It will be omega x plus b equals 0. So I can get this decision line using a perceptron. Maybe your data, it's in 3-dimensional space. So maybe it's we plot the data. We have x1, for example, as a feature. We have here x2 as a second feature. We have also x3, correct? So it's in 3-dimensional space. So in this case, I need to get a hyperplane for dividing my data into two different classes. If I can see that it should be possible to use a linear model for generating this one, I can get this one. So this one will be omega 1 x1, for example, plus omega 2 x2, plus omega 3 x3 plus b equals 0. And also this decision boundary, for example, we can generate this one using a perceptron. So we can just use a perceptron for classifying those simple data sets. There is another set which is different. We call it non-linearly separable data sets or inseparable data sets. This one, it's inseparable because it's linearly inseparable. We call it linearly inseparable, which means it's impossible to find a straight decision line or a straight line to divide it into two different sets. So in this case, this one it's more complex, and it need really more complex model for solving it. So from visualizing the data, it will help us to decide which model we need to select for training for solving this kind of problem. So I have been talking about the pipeline. So the pipeline consists of uploading the data. We need to try to visualize the data, try to use some pre-processing techniques, for example, and after that model selection. And when we select a model, we will divide the data into a training set and testing set. After training and testing your model, we need, for example, to get the confusion matrix to evaluate the performance of our model. So mainly it's like 3 steps. The first step is data pre-processing, model selections, and model training. And after that, we need to evaluate and test our developed model. If you are happy with the model, it's fine. If not, you will go back and you will try to change the model hyperparameters and try to retrain your model one more time and repeat this process until you have good performance. So I will explain the XOR problem. The XOR problem, it's a very simple example for linearly inseparable. Why it's inseparable? Because here we have 2 classes. We have the blue class, right? We have this class, blue one, and the red one. The red one, it's 0, label is 0. And the blue one, the label is 1. So when we look into this table, we have this is class, correct? This one, it's 1 class, and 0, it's another class. So when you look into the data, it's impossible to find a straight line to divide these data sets into 2 different groups, right? If we selected a line here, for example, if I selected this one, what would be the accuracy of this one? I can select this one. I know the features are x1 and x2. I call here x and y. So this line, it could be, for example, omega 1x plus omega 2y, for example, plus b equals 0. So this is my decision line. So when you change omega 1 and omega 2 and b, you can generate different types of lines. Imagine that we selected this line. What will be the accuracy of this line? Points above it, it will be 0. Points below it, it will be 0. So this one, the blue one here, this one and this one will be correctly classified. This one will be misclassified, correct? So in this case, the accuracy will be, because this one is correctly classified, this one is correctly classified, this one correctly classified, this one it's misclassified. So the accuracy now, it will be 3 divided by 4, correct? So the accuracy will be 3 divided by 4, or 0.75, for example. So the accuracy, it's 75%. It's impossible, in fact. When you select a line, if we selected a line like this one, the accuracy will be 50%, correct? So the baseline accuracy here, maybe it will be 50% or 75%. It's impossible to find a single line which will divide these data sets into 2 different sets, one for 1 and one for 0, for example. Minimum, we need to have 2 lines. So 2 lines, for example, if I selected this line here, so this is 1 line, and we can select also this line, correct? So we have 2 lines, all data points which are located in the middle here. So this one, it will be +1. This one, it will be +1. This point, it's 0, and this point, it's 0, correct? So we can say that all points which are located between the 2 lines, it's +1, and points above, it's 0, and the points below it, it's 0. So this one will have accuracy of 100%. So the accuracy of this model will be 100%. So we can just say that it's inseparable because we cannot find a single line to divide the data sets into 2 different classes. We cannot find this line. At least we need to get 2 straight lines. If you want to get 2 straight lines, you need 1 perceptron for generating this one. You need another perceptron for generating this one. So in this case, we need 2 perceptrons, in fact, for solving this problem. And if you can see, this is a confusion matrix. So in fact, we have two cases are 0 classified as 0. This is the actual label, and this is the predicted label. So we have 2 classified as 2, 0, 2 ones classified as 2. So the accuracy really, it's 100%. If we need to generate this model, we need 2 perceptron because each line will be generated by 1 perceptron. So I can just, if I want to draw this model, for example, so I need a perceptron. Sorry. So in fact, we need 2 perceptrons. So I will get 1. for generating the first line and a second one for generating the second line. And I have two inputs, so I need to connect my two inputs to my two perceptrons. I will call the first one it's x1 and the second input it's x2. So I will connect x1 to both perceptrons, and I will connect also x2 to the two perceptrons. And remember, each perceptron also has a weight, has a bias. So this one it's plus. We have here B1, for example. We have here bias. I will call it B2, for example. The weight value here, I will call it omega 1, because it connects x1 with perceptron 1, for example. This one it's omega 1, 2. This one it's omega 2, 1. This one it's omega 2, 2. So the first one, it will generate the first line. The second one, it will generate the second line. But now we want to make a decision, correct? We want to make a decision. So now I can generate, I mean, the first one will generate this line, and the second one will generate this line. But I mean, we need to make decision because I just need a class. I need 0 and 1, right? So in this case, we need to get a third perceptron. So we need to get a third perceptron here. And this third perceptron, it will make decision. It will combine. I mean, the information from B1 and B2, and it will make one final decision. So in this case, we need to get a third perceptron. The output in this case, it will be just 1 and 0, correct? So the output from the third one, it will be just 1 and 0. So now we need to get another weight value connecting perceptron 1 with perceptron 2. I will call it V1, for example. This one, it will be, for example, V2. And we need to have also bias value here, which is B3, for example. This one, it's +1. I will call it B3. So now we build a different model. So when the data set is complex, like this one, we cannot just use a perceptron. It's impossible to use a perceptron in this case because it's linearly inseparable. I cannot find a single line to divide it. We need at least 2 lines. All data points between the 2 lines will be +1. Data points above those 2 lines, I mean above this line, it will be 0. Below it, it will be 0. So we have 2 perceptrons, and each perceptron will generate a decision boundary. We need here a third. We need here to get a third perceptron to combine the decision from, because each one will generate a line, and we need to combine those decisions. In fact, combining those decisions, it means we need to get the intersection. So the first perceptron, it will generate this line. All data points above it, it will be 0. All data points below it, it will be, for example, +1, right? And the second perceptron, it will generate a second line. All data points above it, for example, it will be a class 0. All data points below it, it will be class, for example, 1, for example. Now we need to get the intersection. Why the intersection? Because the intersection will help us to find the area in the middle. So the area between the 2 lines, it will be class 1, and otherwise it will be class 0. So now we need to get this kind of model. This model, it's complex because my data set is complex, all right? So now it's different because it's not a perceptron anymore. It's multi-layer perceptron, in fact. So because we have the inputs connected to this layer. For example, we call it layers. For example, now I have a layer, and this layer has 2 units, and I have another layer, and this layer has only 1 perceptron or 1 unit. So we can just say this one, we can call it multi-layer perceptron, MLP, or feed-forward neural network. Now it's a neural network, or multi-layer perceptron. Multi-layered because I'm using multi-perceptrons, and I try to organize it into layers. So this one, I can call it now input layer, right? I can just call this one, it's my input layer. And the one in the middle, I can just call it, this is hidden layer. And this perceptron in the output, I can just call it output layer, right? So now it's MLP. We use this MLP for solving more complex problems. You can just use it for solving any kind of problems. And I mean, how can we change it? Just increase. You can just increase the number of units in the hidden layer. You can just increase the output. If you have more than 2 classes, for example, I mean, this problem, it's simple. I have 2 inputs and I have 2 classes. So the 2 classes, it's 1 class and 0 class. So now we can solve this complex problem, in fact, using a multi-layer perceptron. How can we solve it in Python, for example? We have something called MLP classifier, right? MLP classifier, this is MLP classifier, we call it, it's from sklearn. So we can import MLP classifier from sklearn, and we need to select the activation function because, you know, I mean, we know from before that each perceptron has an activation function, correct? So we need to select what kind of activation function. For example, we will select logistic activation function. Logistic, it's like this one, right? This Gaussian, correct? So this, I mean, it will convert the input into 0 or 1, right? So it will be like this one. This is a logistic, I mean, activation function. For example, we need to specify maximum number of iterations. We will train this one, so we need to decide how many epochs, for how many epochs. And in each epoch, in fact, we go through the data points, all the data points. We need to specify, if you will select a multi-layer perceptron, you need to specify the number of hidden layers, right? So in this one here, we will specify the number of hidden layers and the number of units in each hidden layer. So we selected 2. When it's only 2, it means we selected only 1 hidden layer with 2 units in this hidden layer. And for the output layer, we don't need to do anything because it will configure it automatically from my data, right? So for the output layer, it will just try to find it from the data when we fit the model with X and Y. It will understand that we have one output, for example. And the value of this output, it will be 0 and 1. 0 for class 0 and 1 for class 1. This is a label, right? You can do it like this one. So in fact, here from this one, this is the output. So the output is 0, 1, 1, 0. We have only one output, and it takes 2 values, 0 and 1. You can solve it in this way, or also you can do it. You can do some one-hot encoding, right? So I can convert to this one, in fact, because it's 0, 1, 1, 0. So in fact, I can convert it into one-hot encoding. So it will be like this one, 0, it will be 0, 0. Sorry, it will be 1, 0. 1, it will be 0, 1. 1, it will be 0, 1. And 0, it will be 1, 0. So I can convert it into 2 columns. We call it one-hot encoding. So you can do it like this, or you can just keep it as it is, right? When it's multi-class classification problems, it's important to use one-hot encoding. Because maybe I have 3 classes. So if I have 3 classes, maybe it will be 0, 1, and 2, right? So in this case, it will be hard for my model, and it's recommended, it's important to use one-hot encoding. So in this case, we will have 3 outputs. So the first output will be 1 when this class is selected, for example. The second one, it will be 1 and the rest will be zeros. Or the third one, it will be 1 and the rest will be zeros, right? So we call it one-hot encoding. So now we build our model. We need to train the model, correct? So we will train it using X and Y, and we will train it using 100 iterations, for example. It's maximum number of iterations. So maybe we will, and also we need to select the solver. We need to select the optimizer. After training your model, you need to predict, right? So I need to use this command, model.predict using X. I need to use the X value for making predictions. Now I have my predictions. You can print the model coefficients. So it will be model.coefficients. And you can print also predictions. You can calculate error. So the prediction error, this one, it's a prediction error. So the prediction error, it will be the number of cases where Y is not equal to Y predict, right? So this is a prediction error. So we need to count the number of cases where the prediction is not equal to the target feature, for example, when Y is not equal to Y predict. And after that, we need to predict, we need to plot the decision line, for example. So the decision line, it's easy. We need to generate some values for X1, right? And we need to use mesh grid, or X1 and X2, in fact, and we need to use mesh grid to generate a grid and apply the model at each point and just plot it. And after that, we can get confusion matrix. Confusion matrix, we can import it from sklearn.metric. So, I mean, for plotting the decision line, and this is, yes. So this is how we plot it. So I just want to inform you how can we plot it. So it will be like this one. We have our data points. It will be like this one. We have X1 and X2, for example. So we have here X1 and X2. We will generate values for X1 from X1 minimum to X2 minimum, for example. And we will generate some values, right, with some step. And we will do the same for X2. And we will generate this grid. And the model which we just trained, we will apply it to each point. So we will send this point, we will predict in which class this point belongs to, this point, all points. We will do it for all mesh grid points. And after that, we will plot it. So when we do this, we will get this nice graph. So all points between this line and this line, it will be class 1. All points above it, it will be another class. All points below it, it will be 0 class. So this is the XOR problem. XOR problem, it's complex problem, and you cannot solve it using a perceptron. And we need to have, we need to build a multi-layer perceptron or a feed-forward neural network for solving it. You can go to this command here. You can go to this line in GitHub in this MLB classifier, and try to make some changes. For example, so try to select. You can select, for example, 2 hidden layers. You can increase the number of units in the first hidden layer. You can make it 3, for example. You can make it 4, and just rerun the code one more time and see if he will get a different decision boundary. I mean, I got this simple decision boundary because the data set is simple. I mean, in the second example, I try to make it more difficult. But if you have any question, please just ask me. Do you have any questions? You can just open your mic and just ask me if you have any questions. Go to this link in GitHub and try to run this XOR one more time. Once we did this, this is MLB. We can use it for any kind of data sets. For example, if you want to apply it for Iris. So for Iris dataset, we have how many inputs we have? We have 4 features. We have X1, X2, X3, and X4. And we have 3 classes, right? So class 1, class 2, and class 3. So you can change it for Iris dataset.
I have a question. The XOR problem seems. Yes, I have a question.
If you don't have any question, I will go to the second example.
Can you hear me?
And after that, we will take a break where you will go to the code and try to run it and modify it for Iris dataset. So in the second part, in fact, I try to make it more challenging for our feed-forward neural network, right? This one also, it's XOR-like data. So it's XOR data also, but I just generated it by random to make it more challenging. I mean, in the first problem, we have only 4 examples, 4 data points. And as you can see, it looks like easy. I mean, it's easy because we can just find this line, we can find this line. So in fact, it's not very challenging to our multi-layer perceptron. If you want to make it more challenging, so I just generated these data points. So in fact, it's the same. If you can look into it, so it's still XOR. This one, it's a +1, correct? This one, it's a +1 class. This one, it's a 0. This one, it's a 0. So it's the same like XOR, right? So it's XOR like data, in fact. So in fact, here I selected k equal 100, and I just select each section is 100 points, and I just add some. I added some offset. So you can see here I plus Q minus Q minus Q plus Q to just generate it looks to generate those data points similar to XOR. So the XOR, it will be like this one. I mean, this is the XOR. This one, it will be, we have 0 0, which will be for example 0. This one, it's 1 1, which will be 0. This one, it will be +1. Yes, can I will just so I cannot hear you, but I will try to know why. all people are muted, which is
Testing.
so.
Hello.
Magnus, you can talk now, I
Yes.
guess.
Hi. Hello. Can you hear
No,
me?
I cannot hear you. Still cannot hear you. Okay, so we need. Yes, Magnus.
Yes. Hello. Hi.
So you can just unmute your
Let's-
mic now, and you can just, if you have any questions, please ask me.
Can you hear me now? Hello. Okay, so it.
You can hear him, but I cannot hear him. In fact, okay.
Can you hear me?
Mic check, 1, 2.
Yep, I can hear you.
Jeg tror alle kan høre hverandre utenom
Ja, det
Yes,
virker sånn.
Magnus. Yeah, I can hear you, Magnus, now. Yes.
Okay, excellent, excellent.
Mhm.
So my question is, it might not work with the XOR, but with the one that you have, or it would work with the XOR if you put on if you shift it around. The thing is, would it not be linearly separable if you do some what's it called again, variable synthesis, was that it, from the previous lecture with
Yes,
if you
yes, correct.
square the values?
Yeah, very good, very good. So we call it feature construction. So if we can
That's the one.
construct a super feature, it will help us, in fact, to make it linearly separable.
But the XOR problem should be linearly separable if you do some feature construction, wouldn't it?
Yes, correct. So it will be the next step, in fact.
Okay, excellent.
So it will be the next step. Because some problems, so we need to try, in fact, we need to play with our features and try to generate new features which can help us to make it separable and simplify the problem. I mean, this, we call it feature construction. So we need to construct super features which can be used for, to make it more simple, in fact, for our model. And therefore, they recommend people to spend the time working with data. In fact, try to simplify it, because when we simplify it, it will be much simple for our model. So we will talk about it very soon. But before leaving that part, in fact, I just want you to remember something. How many weights we have here in this model? So in this model now, how many weights we have? We have 2 inputs. We have one hidden layer with 2 units. We have an output layer, right? With 1 unit. So how many weights? So it's 2 times 2. It's 4 plus 2 bias. In fact, so it's 6. So in fact, we have here 6. And from this one, we have 1, 2, 3. So we have 9. So just remember this number, please. Right? So we have here the number of trainable parameters are 9. We have 9 parameters here, which we need to adjust, correct? So when we are training this model, we initialize it with random values. We initialize all those weight values and bias value with random values. And after that, we will start the training process, and we will try to find the good combinations of those weight values and bias. So, but just remember this number. We have here 9. Why 9? Because we have 2 inputs. The hidden layer has 2 units. So it will be 2 times 2 plus 2 bias. So it will be 6. And for the output layer, we have 3. We have 3 weight values. So in total, it will be 9. So we will go to the second example. And in the second example, in fact, we will just generate this data set, which looks like XOR, and we will try it to make it more challenging for our perceptron, in fact. So this one, it's XOR. It will be like this one. If it is 4 points, it will be easy to just find 2 straight lines. But we try to make it more challenging here. And also, we try to make some overlap between classes. So it will be impossible, in fact, to find one line. So if we selected a line like this one, it will be impossible. If we select to get a line, it will be okay, but maybe the accuracy will be 0.6, 0.7. So we need to know how to do it. We will just apply the same MLB, which we used for the first problem. The same, no difference. So the same activation function logistic. Maximum number of iteration, I will increase it a little bit, correct? And it's only one hidden layer, but I will increase the number of units into 20. because maybe 2, it's too little, correct? 2 will be very too little, but you can try, and we will select the same solver. So it's just copy and paste, in fact. So I used the same model. Everything is the same, identical, except I increased the number of units in the hidden layer into 20. And I just trained the model one more time using this new data set, and I got this very complex decision boundary. Do you see the decision boundary? Now it's more complex, in fact, right? So it's more complex decision boundary. And we can achieve accuracy, it's almost also 100% accuracy. So if you look into this one, I have here, in fact, 200 points, and I have here 200 points. So I have in total 400 points. And if you can see here, all numbers across these diagonals are 0, which means the accuracy, in fact, it's 400 divided by 400, which is 1. So the accuracy here, in fact, it's 100%. But remember, I didn't divide my data here into one for training and one for testing, right? So we just used the whole data for training and the whole data for testing, which is not correct. But it's just to show you. I mean, I'm not talking about training and testing. I'm just talking now about model complexity, for example. So now we can, when we use one hidden layer with 20 units, we can generate this very complex one. In my model here, I didn't use random seed. Do you remember random seed? When we use random seed, when we train the model, we will get the same result, the same decision boundary each time. So when you run this model several times, each time you will get different decision boundary. So here we have different decision boundary. Here we have another different decision boundary. And if you will run it again and again, each time you will get a different solution. Why different solution? Because each time we start from different random values. If you want to get the same, we need to use the same random seed, correct? So, so the accuracy here, it's 100%. I used it with more challenging data sets, and we can classify it using our model. So this model, in fact, it's the same. It's one hidden layer, but in this time it has 20 units. We have an output layer which 1 unit. We just connect, and we have 2 inputs here, x1 and x2, right? So the model here, it's more complex because we increased the number of units in the hidden layer. When you increase this number, in fact, it will be more efficient. Why it will be more efficient? Because it will be more capable. So we need now to count how many width values we need to adjust in this model. Can you tell me, please? We have here 2 inputs, and we have here 20 units in the hidden layer, and in the output layer we have only 1. So can you count how many widths we have? Just please raise your hand if you know, and you can write it. You can just unmute your mic and just answer. Do you know how many weights? Again, I will give you a hint back again to this example. In this example, we have 2 units. We have one hidden layer with 2 units. We have one output layer with 1 unit. So, so the number of weights was 2 times 2 plus bias 2 plus 2 times 1 plus 1. Okay, so Magnus, he said it's 81. Okay, so why it's 81, Magnus? Can you explain, please?
Sure. 20 weights for each of the input. 20 weights for each of the input values to the hidden layer.
So it's
giving it 2 by 20.
2.
Yep.
Yes, correct. Plus
20 weights for each of the hidden layer.
Correct.
20 weights from the hidden layer to the output layer plus
yeah,
1.
Yeah, correct. Very good. So this is correct. So this is the number of weights which we have, in fact. So it's 20 times 2 plus 20 for the hidden layer. And for the output layer, it's 20 times 1 plus 1. So in total, it's 81 weights. So do you see the complexity? So when the data set is more complex, we need really to have more complex model. So we increase the number of weights from 9 for this sample model into 81 for this complex data set. So when the data set is more complex, we need really to increase the number of weights. We need to increase the model capacity. We call it model capacity. So when we increase the number of weights, it means we increase, it's like brain cells, for example. We need to increase the brain cells for our model. So it will be really more complex. It will be more capable. It will be smarter, in fact, because those weights It's a piece of information or knowledge which is a model used to make decisions. Now it's more capable, in fact. It's like one with a PhD, for example, he has a PhD, and we just give him an exam for first year in primary school, for example. So he will be really very capable. He has lots of knowledge. He trained his brain a lot in lots of things. So when you give him an exam in elementary school, for example, he will be just perfect. He will get A, right? So, but what is the problem here now? We want to increase the model parameters. When we increase the model parameters, remember, the model will be more capable, but also you will have a risk of overfitting, right? What is overfitting? Overfitting, it means my model will memorize my data set. It can generate very complex decision boundary here, and it will just able to memorize the data points quickly. So we need to be careful, in fact. When you increase the model capacity, you need to be careful to avoid overfitting. Overfitting means my model will memorize my data set, and it will be able to generalize. So when we test it using a test set, the performance will be really very bad because it will just memorize it. So we need to stop my model from memorizing my data set. So when we train it, we don't need to let it train forever. For example, we need to stop it early. Because if we will keep training, the model will memorize the data set quickly, and it will not be able to generalize. It will not be able to predict correctly. So it's important here, in this case, it's important to divide my data set into one section for training and one section for testing, because I need to test. Because if my model overfit my data, it will memorize my training data points, and I can discover it from its performance with a testing data set. If the performance was very, very good in the training and very, very bad in the testing, it means my model is overfit my training data set. So this is one way. We need to stop it from training. We call it early stopping. So if we discovered that my model overfit my data points, we need to stop training. We call it early stopping. And also maybe we need to simplify the model little bit. So if you have lots of weights, I have 81 parameters here. So maybe we need to put some restrictions on the weight values, right? We don't want to allow the model to just adjust the weights to infinity, for example. We need to put some restrictions on the values which the weights will take, for example. So now we are moving from a simple problem to a more complex problem. So now we need to see the power of feature construction. What is feature construction? Feature construction, it will be like this one. This is my data point, and I plot my data point here between x1 and x2. So I have here x1, I have here x2, for example. You see, this is x1 and this is x2. When we plot the data in this way, it will be more complex. And now I need a model with 81 parameters, right? But if we can do some manipulation to my features, maybe we can simplify it. So for example, here, if you can plot x1 against x1 times x2, it will look like this one. So the brown one, it's a class 1, and the yellow one, it's a class 0. In fact, if we can plot x1 against x1 times x2 plus 1, it will be above. It will be in the above x for x greater than above y. In fact, it will be above the x-axis, and the yellow one will be below the x-axis, right? So it will be like this one, because in fact, that part here, if this one it's x and y, so this one is it's a plus times a plus, so it will stay in that place. If you multiply x1 with x2, for this one it's a negative, so it's a negative times a plus. It will go to the negative section, so it will go back down here. That part it's a negative times a negative, so it will go up here, so it will be positive. This one it's a negative times a plus, so it will stay in the negative part. So if we can plot the data x1 against x1 times x2, it will be linearly separable, in fact. So the data set will look like this one, correct? And this one, it's easy because I can just put a line here. So the task here is to find this line, and we can now it's a straight line, correct? So it's a straight line. So if we need to generate this straight line, we just need a perceptron. I don't need a very complex model. So in this case, I just need a perceptron, and the perceptron will have two inputs. One input will be x1, and the second input, in fact, will be x1 times x2, correct? And I need to have a bias here. So the model becomes very, very easy one, in fact. So the output will be just 0 and 1. And this one, it will be omega 1 x1, omega 2 times x1 times x2, correct? So now we are generating a new feature. We are generating a new feature. And this feature, we can just call it x3, for example, where x3 equal x1 times x2. And when we use x1 with the new feature, super feature, the data set becomes separable, and we just need a very simple model. And can you count how many parameters in this model? How many parameters for this perceptron? You can just raise your hand, or you can just use your mic, you can just try it. How many parameters for this perceptron? Yes, 3, very good. So we just need 3 parameters here. So do you see the difference? When we have been working with this problem, we need a multi-layer perceptron, and this multi-layer perceptron, it requires, in fact, 9 parameters. This is the minimum number, in fact. And when we made the data set a little bit more complex, we need 81 parameters, right? And when we use feature construction, when we constructed a new feature called x1 times x2, we just need a perceptron, and we just need 3 parameters. So it's extremely simple model now. It becomes very, very simple. So you can just imagine how much resources you need, not for this problem. You can just scale it up to any other kind of problem. We need less memory. We need less time for training our model. My model, definitely, it will not overfit my data, because the model is simple. It's just a perceptron. There is no chance that my model will overfit my data points. So working with feature construction is very, very important. Very, very important. When we multiply x1 times x2, it means we consider the interaction between features. Multiplication, it's interaction, x1 times x2. You can use also higher order features like x1 squared, x2 squared. We used x1 squared and x2 squared last time. This problem, do you remember this problem?
I have
We
a
generated
question.
this data. Yes?
So you're saying that since we're only using one perceptron, that means the model is invulnerable to overfitting. Could you
Yes.
generalize that to saying that the simpler the model is, the less likely it is to overfit?
Yes, correct. Yes, of course. But also remember, because you can underfit, right? So if your model is too simple, it might underfit your data point, right? But you will discover it. So if the performance is bad in the training and it's bad in the testing, my model is too simple for my data set. I need to make it more complex. And it's recommended, in fact, to start with a simple model, and after that, you just increase model complexity with time until you have a good solution. Because overfitting, it's a big problem, but underfitting, it's not a problem. So maybe I can start with my model, and I just feel that the performance in the training, it's 70%, and in the testing, it's 72% or 65%. So it's too low, in fact. So in this case, I can just say, okay, I will increase my model capacity. I will add one more hidden layer, or I will increase the units in the hidden layer to make it more complex. You reach, for example, performance of or accuracy of 92%, 95%. In this case, we can just say it's fine. So it's smart, in fact, to start from a model which underfit your data set and increase complexity step by step until you have good performance. And instead of starting with a more complex one, and you just have this overfitting problem, and in this case, you need to go down, you need to simplify it a little bit. So usually people prefer to start with a baseline model and try to increase model capacity or model complexity until you have a good performance. Yes. So when we multiply x1 times x2, we consider here, in fact, interaction between features, but also we can select, for example, you can try higher order features. I can select x1 square, I can select x2 square, right? I can select x1 cube, x2 cube. I can select x1 times x2 square, and so on. So in fact, we should, if you don't know the data set, you can try all different or all possible combinations. So you have the features. Maybe I have 5 features, x1, x2, x3, x4, x5. I can try all possible combinations, and there are some statistical tools which will help you to decide if this new feature is good or bad. If it is good, we can keep it. If it's not useful, you can just ignore it. Yes. So I guess we will stop here now. So we will take a long break. It will be maybe 30 minutes or 45 minutes, for example. I will check. No, sorry. No, it's not now. Okay, we can just take 10 minutes, in fact, or how much time do you want to go through those examples? I want you to go to this example and try to change model parameters here, try to make it different, and try to change, I mean, a different, for example, different decision boundary. But remember, in this example here, we didn't divide the data into training and testing, right? We didn't divide the data into training and testing. So you can just divide these data points. You can use train test split. Do you remember this function? We used it last time. Last time was Iris and was MNIST data set. So you can just use this function, train test split, and divide the data point here into two sections, one for training and one for testing. Retrain the model using the training set and test it with the test data set, and plot the confusion matrix, and also plot the decision boundary. So just you need to add one section here for dividing the data into X-train, Y-train, X-test, Y-test. So now I trained my model here using the whole data set. You need to change this one, in fact, using X-train, Y-train. So you need to add one more line here. It's called train test split. And the train test split, in fact, it will shuffle the data. So it's very important to be sure that, because we have here two classes, and we need to be sure that it's well shuffled, right? So please, we will take 10 minutes break, for example. We can start again at 11:20, for example. Take your coffee and try to repeat this example, but remember to add this function, which is train test split. Yes, thank you very much.